So the next speaker in our session will be Quan from Tsinghua University, who will present his work, together with his collaborators, of course, on building dynamic system called Sandbox with partial order analysis.
Okay, hello everyone. I'm Zhang from Tsinghua University. Today I will be presenting on building dynamic system called Sandbox with partial order analysis. As software systems become increasingly complex, it is inevitable to introduce security vulnerabilities in these programs. Attackers may exploit this vulnerability and further compromise the host operating system. During the attack, attackers rely on some security-sensitive syscalls, such as exif. To mitigate such attack, security researchers start to employ the syscall sandbox to isolate programs. Syscall sandbox can restrict the syscalls that a program can invoke according to a customized policy. With an appropriate policy, the system sandbox can permit the necessary syscalls for the program normal execution, while also limiting the necessary syscalls to mitigate the attack. Therefore, numerous recent works perform advanced static analysis to identify the minimal required syscall set for a program. However, many critical syscalls are initially required by a program, so they are also permitted by existing works. For instance, Nginx requires the syscall setuid and exif, which can be used for remote code execution and privilege escalation. Consequently, even with the syscall sandbox, attackers can still exploit the CVE 2016-0746 in Nginx, compromising the operating system. Nevertheless, we notice that a program required syscall set reduces throughout its life cycle. For instance, the figure shows the life cycle of Nginx. During its life cycle, it is found that the need for exif diminishes once the master process begins in the third phase, and the set UID will be invoked for the last time during the initialization of worker process at the fifth phase. If we adopt a dynamic syscall sandbox that can adjust the syscall policy along the program execution, we can reject the syscall exif and the set UID once they become unnecessary. In this case, even attackers can exploit the CVE at the sixth execution phase of Nginx. They cannot damage the operating system with limited available syscalls. Therefore, by dynamically adjusting the syscall sandbox policy according to the program's demand during its execution, we can effectively mitigate the attack. However, formulating a dynamic syscall sandbox policy is hard, as identifying syscall reduction positions where a syscall becomes unnecessary is challenging. Existing work may manually identify one or two transition points or programs' different execution phase to set the policy, such as the beginning of program's initialization. Nevertheless, such manual identification requires expert experience and extensive efforts, making it impractical to analyze a program's entire life cycle. Therefore, in this paper, we introduce Sandbox, a dynamic syscall sandbox that can adjust the syscall policy during the program's execution. First, it employs partial order analysis to automatically identify the syscall reduction positions where syscalls become unnecessary. Then, at these positions, we perform the implementation during the program's compilation. In detail, we leverage Linux syscom and LibSyscom to construct the syscall sandbox and adjust the policy. Syscom is a mechanism provided by Linux, allowing a program to set a customized syscall sandbox for itself. It provides a monotonically decreasing permission model that allows the program to only make the policy more strict. Moreover, Syscom sets an independent policy for each thread, where a child process or thread must inherit his parent's policy. With Syscom, we perform the implementation at each reduction position of the program, appending a new rule to Syscom to restrict the corresponding syscall. As the figure shows, at two positions, we call Syscom add rule interface to restrict exif and set UID respectively. After implementation, a physical enhanced binary is produced. Then, during execution, it will trick the affirmation code at the proper positions by itself, restricting the exceed and set UID. Hence, the most critical part of Sandbox construction is identifying the physical reduction positions for which we propose a partial order analyze. A physical reduction position is a pair of adjacent instructions. As the figure shows, if the program executes I1 and jumps to I3, then the physical exceed will become unnecessary. Therefore, RI1 I3 is a physical reduction position for the physical exceed. To identify the physical reduction position, we should locate the position where the required physical set reduces. A required physical set for instruction II includes all the physicals that are invoked by II and II's subsequent instructions, which is calculated through the mapping phi. From I1 to I3, exceed is removed from the required physical set. Next, we further convert the problem of resolving required physical set to the problem of determining execution order of instructions. Here, we define the successor relation of 4 instructions. If ij successes I, then there should exist at least one execution trace where ij is executed behind I, or ii equals ij. In this case, ij is termed as the successor of ii. If we can establish the partial order of instructions with the successor relation, where each pair of instructions has at most one determined relation, we can easily identify all the physical invoked after any instruction, thereby resolving each instruction's required physical set. For instance, we resolve the successor relation of I1, I2, and I3 and exceed, finding that the exceed will not be invoked after I3. Therefore, the main intuition of partial order analyze is to establish the partial order relation of instructions. In the workflow, the analyze first builds a candidate graph according to the program's control flow. Then, it transfers the candidate graph to the partially ordered graph, on which it establishes the partial order relation of instructions. Next, based on the relation, the analyze resolves the required physical set and the reduction positions, finally constructing Sandbox with proper instrumentation. Next, I will introduce each step in detail. In the first step, we build a candidate graph whose nodes are candidate set reduced instructions. A candidate set reduced instruction is an instruction after whose execution the required physical set may change. We found that such instructions fall into 2 categories. The first category is a system invocation instruction, as a syscall may become unnecessary after its last invocation. It is found that programs typically invoke syscalls through some libraries' high-level interfaces. For example, printf from libc invokes syscall like write and fill text. Therefore, we utilize the Angular to preprocess each library's binary to resolve the syscall invoked by each interface. The second type involves jump instructions. Since after the program jumps to one branch, some syscall on other branches will become unreachable. A program typically contains both intra-procedure and inter-procedure jumps. Intra-procedure jumps are usually caused by statements like if and will. Inter-procedure jumps are typically function calls and returns. Moreover, some programs may invoke indirect calls, for which we utilize SVF to resolve the targets of indirect calls. After collecting all candidate set reduced instructions, we connect them according to the program's control flow. Finally, we obtain the candidate graph, which can over-approximate the possible execution trace of program. Specifically, for any possible execution trace, we can find a corresponding traverse path on the CG. Next, we transfer CG to the partially ordered graph, denoted as PG. The transformation is performed based on the mapping mu, which correlates each set reduced instruction II in CG to a node NA in PG. The mapping is shown as the equation below. First, the analyzer utilizes the function is in cluster to conduct critical sniffing, mitigating the precision degradation caused by illusory traces. Since the building of candidate graph does not consider the context of function invocation, it may introduce some illusory traces when approximating programs' possible execution traces. To address this, we cluster the instructions of a function in which no courtesy calls are invoked, such as the log function shown in the figure. In this way, we can restrict this courtesy call timely, though it may delay the restriction of other syscalls. After analyzing extensive malicious payloads, we summarize the frequently exploited syscall as courtesy syscalls. They are usually related to network operation, permission control, and common execution. Then the mapping is performed based on the traversed paths of CG. If two instructions on CG are mutually reachable, then the two instructions will be mapped to the same node of PG. For example, the figure shows a while loop where both two instructions are mapped to the node N4. When all candidates that reduce instruction in CG are mapped to nodes of PG, the edges from CG are transferred to the PG accordingly. Finally, as the figure presents, we obtain the partially ordered graph. In the graph, node log is the cluster node for all instructions of the function log. Two instructions of while loop is mapped to the node N4 in PG. On PG, we can prove that its nodes are partially ordered with the successor relation. It indicates that each two nodes have exactly one successor relation or they have no relation. Oh, sorry. Therefore, as the right part of figure shows, we can easily resolve the required SQL set for nodes of PG. Next, the required SQL set of nodes can be leveraged to over-approximate the required SQL set of instructions. Specifically, we can prove that if instructions I is mapped to the node NA and I is not clustered by critical syscall sniffing, then the required SQL set of instruction II is a subset of the node NA's required SQL set. In this case, we can ensure that the resolved required SQL set of II includes all syscalls that are needed for program's subsequent execution. Then, based on the required SQL set, we further identify the reduction positions where syscalls are determined to be unnecessary. Finally, with these positions, we construct a customized sandbox for the program. In our paper, we prove that the analyze is sound and the sandbox will not interfere with program's normal execution. The evaluation is performed on 7 complex applications. We evaluate all test suites of applications to validate that sandbox does not interfere with their normal execution. Since sandbox permits different syscalls at distinct execution positions, it is important to evaluate sandbox at applications' different positions. Thus, we gather 43 critical vulnerabilities on all applications and identify their exploitation positions, calculating the average results for each application among all its exploitation positions. We also perform the overhead evaluation, where sandbox incurs 5.07% average runtime overhead on 7 applications. In effectiveness evaluation, sandbox rejects 23.50 and 16.86 more syscalls than Chestnut and Temporal Specialization. Meanwhile, it mitigates 15.88% and 8.90 more payloads. When concentrating on the critical syscalls, as the red boxes show, sandbox can restrict many critical syscalls at proper execution positions where existing work can only permit them during the program's whole life cycle. In case study, we show how the number of permitted syscalls varies during the index execution. As the figure shows, during whole life cycle, Sandbox adjusts the syscall policy for 13 positions, which is impractical for human identification. Moreover, Sandbox rejects many critical syscalls dynamically, such as exif and setuid. Lastly, Sandbox properly handles the multiprocessing program without causing crash. In conclusion, we propose Sandbox, a dynamic syscall sandbox that restricts programs unnecessary syscalls during its runtime. Then we design the partially ordered analyze in which is sung to build Sandbox. Finally, we evaluate that Sandbox outperforms existing measures. That's all. Thank you.
Thank you very much for the presentation. Questions?
Hi, I'm Jiaguang from Rochester. So good work. I think you mentioned this briefly, but I want to ask you again. How do you identify the original system calls? For example, you have in the application, we usually don't call system calls directly, right? We call libraries, especially for C programs, usually from libc. So like you have a fread, then how did you find this fread, fwrite, this kind of, find them by hand or some automatic tool?
We pre-process these libraries. We analyze the libc and other dynamic libraries to identify which syscalls they are used for each interfaces as pre-results and for our analysis. So during the analysis, we locate the invocation of each library interfaces, and we know which syscall are used by this interface. This part of analysis is performed with Angular, a static analyze tool.
Okay, so you use Angular to do for the binaries, and you use that to do some binary instrumentation for your policy, right?
No, we will not instrumentation the binary of libraries. We only instrumentation the code of application.
Oh, application. Then okay, you don't do anything for the directly linked binary library.
Yes.
Okay, that's fine. Yeah, that's actually related to my second question. So in original C code, sometimes it's not common, but you can call system calls directly using assembly language. Do you handle this case?
Yes. They usually invoke the C call with some specific code like syscall or yes, we handle this special situation that some program may directly invoke syscalls. But actually, in this application, we didn't meet that situation.
Okay, we can talk more offline. Thank you.
Okay, thank you.
I would also have a small question. So you presented your work in a context of safety analysis or for exploitation. Would it also enable optimizations in the case of a virtual execution environment?
Excuse me, the virtual execution.
Yeah, so if you run your programs in a virtualization container of some form, so would this also enable some form of optimizations, like reducing the size of the system layer or something like that?
I think this technique can be utilized under this containers or such as virtualization techniques. But each process is specific for a program. So usually those containers or virtual machines are designed for universal programs and not specific for one program. So this analysis is performed for each program. And if you determine that your container is only used for this program, so you can use this to customize a policy for the program.
Thank you. Thanks again for the speaker.